66 centimeter line right here. That point experiences a acceleration equal to g at that point, right here, this point. Now, this only holds true if I hold it from the end. If I hold it from a different point, well, then you got to develop the general equation, depending on where you hold it. Then you got to analyze the problem based on where you're holding it, you see. Now, how about if I do the same kind of thing with a non-uniform rod? Remember the rod that we had from the other day, lambda equals x cubed. Okay, let's see how would that work there. Let's look at, let's come over here, look at the non-uniform. Again, let's hold it from a general place. And then for that one, the center of mass was 4/5 of the distance up to the top, right? So the center of mass was way up here. 4/5 L. Center of mass was 4/5 L of the distance from the end. And then let's say this distance is d again, right? So let's develop the same, go through the same arguments to develop the equation. The torque is equal to I alpha. The torque is equal to d mg sine of theta. And then the moment of inertia, what was the moment of inertia of that rod? About its center of mass. I forgot. So you could look at your notes. I remember it was a small number. Two 75ths. Is my memory right? Good. Is it? Oh, that's not bad. 2 75ths ml squared. But we got to now shift from the center of mass down to there. So plus md squared. Okay. Times alpha. And then when I set this equal to 1, that gives me the maximum angular acceleration. So I get mgd divided by 2 75ths ml squared plus md squared. Okay, so that's my general formula for alpha depending on where I hold it. So again, if I hold it at the end, then d is going to be, if I hold it at the end, then d is going to be 4/5 L, right? So if d equals 4/5 L, then you can put it into here and calculate what the alpha is. Okay. So what does that come out here? Let's do it over here. Okay. Now what's this? 16 plus 2 is 18. No, hold on. This is times 3. This is times 3, right? So 75, 75, 48 plus 2, 50 over 75, which is 2/3, right? So we have mg 4/5 L over 2/3 ml squared. M cancel, L cancel, and then you get here alpha max. This is a great test question, by the way. Hint, hint. Okay. So what's my alpha max? We have 2 goes into there twice. 2 over 15. G over L. So my maximum angular acceleration for a non-uniform rod held at the end, okay, is 215 GL. It seems like it's less than that one. Oh, this is much less, yeah. It looks pretty small, huh? 4/5 L. Somehow it looks so small, 2/75. More torque. Oh, okay. Did I make some algebraic mistake?
No, the calculation.
Where?
4/5 over 3.
2 goes over 2 over 15. Oh, you know what? Yeah, you're right. This one is 2 times 3, 6/5. Now, you see, I'm doing calculus, advanced calculus and stuff, and couldn't do fractions there. Okay, so 6G/5L. So now, compared to that one, 3/2 G over, okay, so it is a little smaller than the 3/2 G/L for the uniform rod, okay? So now I could also answer the question, what's the A tangential of the center of mass, A tangential of the end? A tangential of the center of mass would be the alpha. I would take the alpha, or you're always using the formula R alpha, and then R in this case would be 4/5 L, the distance from the center of mass to the where it's pivoted, times alpha, which is 6G/5L. And then you end up with 24/25. Ooh, almost equal to G times G. So in this case, interestingly, the people sitting at the center of mass of this rod, 4/5 of the distance from the end, they will experience an acceleration almost equal to G. Now, the way you can achieve this kind of a ride is have the instrument is here, and then put the little kids down here, and then you put chairs like this, and then the real big guys are up here. Okay? So that's kind of the mechanism of what's happening here. You can have little small kids like the 1-year-olds are here. No, I'm just kidding. You wouldn't put a 1-year-old there, okay? But the little kids are here, and then as you get over here, you got the big, heavy ones. So the distribution of mass is over here, center of mass, okay? So these people here have an acceleration almost equal to G, and then the people at the end is L times 6G/5L, and then L cancel, and then you end up with 6G/5. Again, it's an acceleration greater than G, but it doesn't match, it's not as high of an acceleration as the uniform. Okay? So the other uniform one, they accelerate faster. Now, if you want these people to accelerate fast, here's what you could do, but this is kind of not evil if you do this. You could put the big guys over here, okay? I'm giving you future engineers here little ideas. You could put the little small kids over here, and then put the big guys over down here, okay? Now what's the acceleration going to be? The center of mass is going to be here. I believe here these people are going to accelerate so fast, maybe twice G, okay? Because what's going to happen here in the formula is you're going to have 2/75 ml squared plus m, and the amount of the shift here is going to be this little amount, okay? From here to here, if you pivoted about that point. So So that's going to be